Hi, I'm James Sykes, CEO and President of Baselode Energy Corp. Thank you very much for watching this presentation. I've kind of digressed from where I wanted to get to with the last video, but since we've recently completed our airborne gravity results over Catharsis and Hook, I thought it'd be a great idea to get all of our investors caught up with what's happening at Catharsis especially, and see how the recent gravity results fit in with our technical expertise. And so, speaking about our technical expertise, I would like to take the opportunity to introduce my technical colleagues to you guys. So with me on this video is Mr. Cameron McKay, our projects manager, and Mr. Omar Atik, our junior geologist.
Cameron? Hi, I'm Cameron McKay, geologist and projects manager for Baselode. A little bit of background on me. Following completion of my undergraduate and graduate studies at the University of Saskatchewan, I spent the next sort of 5 to 7 years with Pure Point Uranium, working primarily on the Spitfire prospect. I was integral in delineating that prospect and also understanding the structural controls of that. And now I'm on full-time with Baselode and happy to be here.
How's it going, everyone? My name is Omar Atik. I am the junior geologist at Baselode right now. I've been part of the team for the last 4 months. I'm a recent graduate from University of Saskatchewan. I have experience working for the survey as well as SSR, where I did a little bit of work for a gold project. I'm mostly in charge for looking over a lot of the historical work done on all our properties. So that's how I've contributed to what we're about to show today.
All right, disclaimer, guys. Here we go. So Cameron is our QP. Next slide. And don't forget, viewers, that we do the OR group, or I guess Baselode is part of the OR group, which is a large umbrella. And you can find a lot of these educational videos from each of the companies, especially Baselode, on our YouTube channel. So just go to the OR group YouTube channel. All right, Cameron, take it away.
Just a quick outline of what the presentation is going to be about today. So we're focusing on the Catharsis project. We're going to talk a little bit about our exploration model, the Athabasca 2.0 model, where we staked and what drew us to the area, what have we identified so far, the historic work that we've done, a recent airborne gravity survey results, why did we do it, and what do the results mean, and our next steps for exploration, including a planned VTEM survey, ground prospecting, and diamond drilling. So the Catharsis project, you can see circled here, it's 100% controlled by Baselode. It's over 83,000 hectares, located at about 60 kilometers south of the Athabasca Basin edge. So we're going to talk a little bit about the geologic setting for the Athabasca 2.0 model. This basically is easily accessible basement rocks with little to no sandstone cover, which ultimately equals that it's a mineable setting. So James has developed this idea, and I've kind of put a little bit of my own understanding on this, and a little bit of spin on it as well. But what we want is deep structures on trend with known high-grade uranium deposits. And so when I started thinking about this Athabasca 2.0 model that James developed, the first thing that came to mind was, shouldn't that be Athabasca 1.0? Because if you look at the history of uranium mining in Saskatchewan, historically, what we had was mines that were developed that were accessible through open pit mining and conventional underground mining methods, whether that's stopes, accessed by declines or shafts, but we didn't have to deal with this Athabasca sandstone cover. So historically, in the Beaver Lodge domain, there was over 18 mines that had produced over 70 million pounds of uranium. Most of this came from the Eldorado, Ace Fay, and Gunner systems. And then Key Lake, James had originally had this under the Athabasca 1.0, but I think it actually does fit in with the 2.0 because it was a conventional mine. You had open pit and underground. So I think it fits in better with 2.0. And then the Northeast Athabasca deposits that are part of the McLean and Rabbit Lake systems. There were 6 mines that were developed there and over 250 million pounds of uranium that came out of there. And then this one here, we'll put a little asterisk beside it, Clough Lake. It was able to be mined conventionally with open pit and underground, but that was due to a serendipitous asteroid impact in the lower Cretaceous that exposed those basement rocks and made it amenable for open pit and underground mining. So from this Athabasca 2.0 model, over 580 million pounds of uraniums have been produced. So I guess the question is, what happened? And what happened was the discovery of the 2 supergiants, McArthur River and Cigar Lake. And these are massive, massive deposits. McArthur River with proven probable reserves and past production of over 650 million pounds of uranium at an average grade of 7%. Now, there are a lot of spots that are much, much more high grade than this in the McArthur River system, but a huge deposit. And then also Cigar Lake with proven probable reserves and past production of over 300 million pounds. And so from these two mines, they over the last couple of decades, they pulled out over 425 million pounds of uranium from these two alone. So I guess, again, what happened was, well, after the discovery of these two supergiants, the focus for exploration really centered around deeper parts of the Athabasca Basin. And so from 1972 on, there's been many, many deposits found, including Dawn Lake, Christie Lake, Wheeler River, Rough Rider. The list goes on. Over 650 million pounds of uranium has been identified in the inferred category and above, and none of it's gone into production. I would be remiss if I didn't point out the Patterson Lake area, where the Arrow and PLS deposits have been recently discovered with over 470 million pounds in the inferred and above category. But if you total all this up, there's over 1 billion pounds of uranium still in the ground in the Athabasca Basin that's not gone into production.
So Cameron, I'm going to quickly stop you there on that, just to weigh in on a couple things. You're absolutely right that you nailed it on the head. Athabasca 2.0 really is more about the mineability. And yes, Key Lake should fit in that model because it was such an easy mine, as were the Collins Bay deposits. So excellent point on that. Athabasca 2.0, no, I'm not actually the guy who did come across it. As you know, that kind of followed along the footsteps of Roger Wallace and Bill Kerr. Awesome. They have that awesome presentation, which I think we should maybe update on our end just to show investors of where we're coming from. But the thing I really want to point out, it's these super deposits, McArthur River and Cigar Lake. All right, let's look at the situation now. Cigar Lake is actually producing. McArthur River is not. Why do you have McArthur River, which has all of the infrastructure, they've mined out 250 million pounds plus, and yes, it was extremely high grade, over 20%, but now they're sitting there with 650 million pounds of uranium, and it's at 7%, which is still incredibly high grade. Why is that on care and maintenance? Now, I'm not expecting you guys to answer. It's more of a rhetorical question, but from my perspective, and I don't know if this is part of Cameco's plan or not, I'm just saying this is from my perspective, is that to get underground with those type of mines, you need greater than 7%. You need to have at least 10%. And maybe this is why McArthur River is on hold. Obviously, unless the share price, the uranium spot price, continues to accelerate and reach higher prices, then McArthur River can go ahead. But from first glances, to get down underground in the Athabasca Basin, the whole unconformity model, you need super high grades.
Yeah, I completely agree, and I think that the takeaway is just the technical challenges of mining these deposits, whether they're supergiant and economic or not. It's very, very complicated when you have all that watering and you have to put up the freezing and all that stuff. So if you can find a deposit that's amenable to open pit or conventional mining, like you're definitely way ahead of the curve. So I think that the focus needs, and what we've done, and exploration going forward, needs to refocus on mineability and not just grades. Okay.
So how does Catharsis fit into this? How does Catharsis fit into this whole model?
Okay, well, let's move on to that. So, the next question in the presentation here is, so is Catharsis too far outside the basin? Because obviously the basin appears to be very important, and we're going to talk about that. So why did we stake it if it is so far outside the basin? Isn't the basin important? And the answer is, well, yes, the basin is extremely important. So the low temperature fluids associated with the Athabasca Basin are critical to uranium deposit formation. There's some debate about the source of the uranium, whether it comes from the sandstone or whether it's from low temperature fluids percolating into the basement and setting up these hydrological convection cells and then leaching uranium in the basement and bringing it back towards the unconformity. And we don't need to have that discussion here today, but there's no debate that the basin and the basin fluids are essential to forming unconformity associated uranium deposits. So then the question becomes, well, what was the original size of the Athabasca Basin? So the Athabasca Basin, by best estimates from the data that we have, is formed between 1.8 and 1.5 billion years ago. And in the intervening time period, there have been many, many glacial events that have scraped off parts of the Athabasca Basin. So there's lots of estimates that vary widely about how much sandstone has been scraped off by glacial and erosional events. But a pretty conservative number would be 2 kilometers or more. And so then there's many people that contend that the Athabasca and Thelon basins, the Thelon Basin being in none of it, were once a continuous basin. So what was the original lateral extent of the basin? We don't know for sure, but we do have some indicators.
Yeah, and that was brought up in that last video that I did, kind of showing the extent of what the Athabasca Basin could have been compared with the with an analog from the Himalayas today. And it really does look like that the Athabasca would have covered where our properties are, especially Catharsis and Shadow. Now, one thing that I will also note is from the I know a lot of our industry peers, they estimate how far the Athabasca actually went out based on the slope of the unconformity that they're seeing near the edge. However, if you do look at a lot of basin architecture, and even what you're showing here in this image, right above Wollaston domain, you can see the sandstone, right where that red dot is. You can see the sandstone actually flatten out. And basin architecture actually has that quite a bit, where you get these extra level of plateaus. So I don't think that there is, I think that this scenario where our properties are over or would have been covered by the sandstone is extremely highly likely.
Yeah, I agree. I don't know that using a consistent slope and just assuming that it was one basin is a good way to look at it, because we know that there were other sub basins, so there would be spots where things were deeper in the past as well. So I completely agree about the basin architecture. And here's an example of that, actually. So this over here, this little piece over here, is called the Riley Sub Basin, and it is part of the Athabasca supergroup, and it is about 85 kilometers away from the current basin edge. And if you take a point somewhere near the center of Catharsis, it's about 85 kilometers. So I don't think it's too much of a stretch to think that we had Athabasca sandstone cover over top of Catharsis during the ore forming phase of when uranium deposits were formed. So the next point about Catharsis is that it straddles the western Wollaston and Mujatic domains, and this has been proven to be a very bountiful trend for uranium deposits. So you can see it basically runs along right here, and all the mines and deposits sort of line up there. And if you take a look at the airborne geophysics, it shows up beautifully as this blue stripe, this magnetic low, and Catharsis sits there right in the middle of it. And so it's very underexplored because it is outside the basin. And there's no present-day sandstone cover, so it makes it very amenable to that Athabasca 2.0 model if we discover something. So the next thing we want to talk about that's important for uranium deposits are very deep-rooted structural systems. And so we look at this map here. You can see the Catharsis project outline there, and you can see Key Lake up there at the edge of the Athabasca Basin. And you'll notice that you can see some interesting lineaments in the magnetics here. And we took the data available on the Saskatchewan Geologic Atlas, and you can pull off known conductors that have been identified from previous work. And you can see all of these conductors that plot here. We then went in and did some digging in the historic work ourselves and found some that don't show up in this data set. So you're going to see a few pop up on the south part of Catharsis and on the north part of Catharsis. So I hope you saw those show up there. And what you can sort of see is there's this trend coming from Key Lake. It runs something like this. And then there's another one that's been well established that runs something like this. And the northwestern part of Catharsis has never had any detailed modern EM done on it in any sort of large scale way. And we think that when we go and complete that work, we are going to end up finding more conductors that sort of complete this lozenge shape right here.
Looks like a perfect shear structure to me.
Yeah. And so this is just something else to consider too, is that we have sort of the closeology of having Cameco in the neighborhood. They just recently staked this ground too. So just some food for thought that we might be onto something.
Now, the history of Cameco and why this is kind of important though, is that Cameco for the longest time, it's been their mantra that uranium has come from the sandstone. If you look at all their properties, they've been focused within the sandstone for years, decades even. So now, why all of a sudden, but dating back to 2019, 2020, so that's very recent, why have Cameco finally boldly stepped outside of the Athabasca Basin? Is it because that, yes, they do realize that the basin was a lot larger? Are they looking for these basin-hosted deposits too, this whole Athabasca 2.0 model? So seeing this, and we've done our own interpretations, and we think that we are seeing similar structures and that are on their properties. That I would say that Catharsis is in the right area, that we are following the right path forward. And Cameco did stake their properties first. Yes. Does that mean they're better than Catharsis? Well, heck no. No, I think we've got a wonderful property, and you guys, we've seen the structures They're beautiful. There's a lot going on for Catharsis that I just haven't seen anywhere else between here and Key Lake.
Right. So now we're going to move on to some of the historic work that Omer has been instrumental in identifying for us on the Catharsis project. So the first thing is this location up here where we did uncover some conductors that have never been drill tested. And we think we're going to find more. There's a high grade uranium showing up here. It was from a grab sample, but it's very important to note that this was from a metasedimentary rock. So lots of times you'll see people come up with flashy high grade numbers, but what they've gone and done is high graded a pegmatite or something like this. This is actually from the type of rocks that we would expect to find a high grade basement hosted uranium deposit. So it's shear hosted in metasedimentary rocks. That's exactly what we're looking for. And it's never been followed up.
If it's okay with you, I would like to add a couple of things about that sample right there.
Sure.
So in the north end of the property where the work that was done, it was done on a very small block, and the sample was taken in 1984. So even the technology they had at the time was very limited. They did do an electromagnetic survey over the property, and the conductors you can see behind the stars, that's where the conductors came from. These are the conductors, as Cameron previously mentioned. We kind of expect these conductors to carry on in our property all the way through. So, which is super exciting. And even the outcrop that they took the sample from, it was outcrop. It was a single outcrop that was close to a muskeg, and everything else close to it was covered. So this is kind of all they had access to. So they don't really know the source of the outcrop, the size of the outcrop, because the limited tools they had at the time. So we were very excited about going in and kind of with the survey information we get, kind of process it, see what structures are doing in the area. So this is one of the things that excites us quite a bit. I'll let you continue, Cameron. Sorry, go on.
Omer,
Yeah,
you
thanks,
actually
Omer.
just sent shivers down my spine.
Okay, so some more historical work that's been done on the property. There has been a fair amount of work that's focused on this Key Lake conductor that's mostly outside of the work that's been done has been focused outside of the Catharsis property. But there has been some drill holes that have been done and some airborne radiometrics and follow-up ground radiometrics. And you can see there's quite good radiometric anomalies, both from the air and from the ground. And from the drill holes that were completed on the Key Lake conductors, there was some interesting results that came back. You have numerous samples that have greater than 0.1% uranium. And also there's some interesting thorium uranium ratios that point to hydrothermal alteration in the area.
And for those thorium to uranium ratios, I just want to quickly point out that we looked at over 250 samples, and only 10% of those samples, or sample results, and 10% of those sample results did have thorium uranium ratios that could be indicating hydrothermal alteration. The other thing to note about those sample locations is that they seem to lie along preferential northeast structures.
Good, yeah. So these are the kind of the highlighted areas where there's been the most work on the Catharsis project, and then some of the anomalies just zeroing in on where the strongest anomalies show up.
But what I'm seeing right there in these maps is that this property is completely underexplored. Yeah, you've got a little bit of snippets to the south of the property, but basically I don't think that's really meaningful work that has been completed, and this is where we have taken the approach to really dig hard and dig deep into it.
Yeah, I agree. And there's only been, Omer, you can correct me if I'm wrong, but I think there's only been 2 drill holes on the property.
Yes.
Yeah.
So they are in the southeast corner.
Yeah, I'm not sure if anyone can see my mouse.
So
kind of right here.
Most of the work that was done on top of our property, at least in the south end of it, this was done by Sunlight Oil, and they were actually not looking for uranium. They were actually looking for nickel and copper at the time. But a lot of the information that they had was over our property, at least in the southeast corner. And it helped us kind of build a better picture, get a better understanding of what's going on in the area. And just the fact that we were able to ground check a lot of the rock types that we thought were in the area, like peelites, semi-peelites, which was super exciting as well. So yeah, anything in the northwest hasn't been touched at all. There has been no groundwork. The only groundwork that was done on that side of the property was a survey, geological survey from Saskatchewan that was done to map the area. But even with that, there are barely any stops. It's a very vague survey. So it's the unknown that excites us the most. And with the pieces that we have, so a lot of the work we did was to build a better understanding of what's going on around the property, because that's all we had. And it just, the shear zone you see in the east side, where we have those white boxes where you can see those zones of mineralization, you have mineralization on surface, which has uranium values in it, which is a really good sign. We are in a uraniferous area, as well as drill holes. They had peaks in radioactivity, nothing too significant, but enough to let us know there's uranium in the area with the right kind of fluids and the right kind of structures. We could find the mother lode.
Fertile uranium corridors, and that's exactly what we're seeing here.
Yeah, that's exactly right. Yeah, the fertile uranium corridor and highly underexplored.
Yeah, and structures, plentiful structures.
Okay, so then now we're going to move on to our recently completed gravity survey and the results and logic behind of it. So like I said, this was just finished, and it was an airborne gravity survey, and this allows for fast acquisition of high resolution data. There's no land impact. So the two things that the gravity survey is really good at is, number one, it's good at highlighting structures. Like you see government academics and university academics using large gravity data sets to highlight things like plate tectonic boundaries. And so it's very good at structures, but then on the small scale, it's good at picking up density contrasts, which basically can be indicative of hydrothermal alteration. And then this helps us focus our target locations. So I kind of answered that a little bit, but why do we use gravity for exploration? So hydrothermal alteration changes the density. You can see this beautiful picture here. There's this metapelite, there's a fresh example, and then a highly altered example. And so these uranium systems are hydrothermal systems. And you have a lot of fluids pumping through these rocks, which obviously is going to change the density of the rocks. And we can pick that out in the gravity survey. So here's a couple of historic examples of where your gravity surveys have been used as a vector to find mineralization. So this is from the Rough Rider deposit. You can see there's this nice gravity low anomaly over here, and it's also coincident with an EM anomaly. So this is a common theme where you have these gravity anomalies that layer on top of another data set, in this case EM, and we also use magnetics and radiometrics. So the idea here is we're gaining a data layer, and then we're going to put that on top of other data layers to help focus our exploration. Here's another example from the Raven Horseshoe deposits. Again, gravity anomaly coincident with an EM anomaly. And here's another example from the Northwest Athabasca. You can see all these bullseyes and elongate trends. And lo and behold, here's a nice example from some drill core there, massive clay alteration, which again equals a change in density. And here's an example which many people will be familiar with, the Arrow deposit, this beautiful gravity anomaly, coincident with a break in the EM, and we all know how that one turned out.
So I've basically seen, I've been on all of those properties. I've seen the gravity work fantastically, and for me, it's been my go-to tool, and that was our technical team at NextGen. We used gravity, we used that combination with EM, and Arrow was basically our favorable target. Now, in all of those examples that you just showed, those are all ground gravity surveys. So just out of curiosity, Cameron, can you kind of mention if there's any benefits to doing airborne versus ground? You did mention earlier that the timeliness of acquisition with doing airborne is excellent. However, do you lose anything by doing an airborne survey versus ground?
The main thing that I think that you lose is there's a lake effect. And so when the ground survey teams are going out and collecting their gravity readings, they'll take lake bottom soundings and like drill a hole in the ice in the wintertime and figure out how deep lakes are, so you can filter off the lakes a little bit better. That would be the main advantage. I've seen comparisons of airborne layered on top of a follow-up ground survey, and you absolutely get the same trends. So yeah. I'm quite confident in the use of the airborne technique. And like I said, the fact that you can do it so quickly, gather so much data, and there's zero land impact, I mean, it's a really big selling feature.
Yep. Awesome.
Yeah.
Fantastic.
So with the collection of the gravity data in the airborne, we also at the same time collect magnetic data, which is great. So this gravity survey was flown on 2 separate blocks on Catharsis. The reason that we did that is because looking at the publicly available data, we could see that the dominant structural trends for the north end were going to the northeast. So you want to fly perpendicular to that. And in the south, they're going more east-west. So again, you want to fly perpendicular to that. So this is the north block right here. And from the mag, what we can see is we have a north structural domain and a south structural domain. And both of these are characterized by these linear magnetic highs and lows. And we know from government mapping and from other company work in the area that these correspond to our metasediments. And then in the center here, we have this regional sort of magnetic moderate to low. And this we know to be a large granitic block. And so what we see happening from this magnetic image is that we see the structure moving like this. So we have this shear system where we have the metasediments that are basically being squeezed against this rigid granitic block and they're sort of flowing around it. And then what happens is that as these two, as this granitic block is rotating, it starts developing these structures that run through it like this. And those are essentially a Riddell type structure.
Now, I'll point out here that the same structure that we see here was the basis for staking shadow. This shadow was on a much larger regional Riddell. This is the same system at a much smaller scale, but again, the same physics, the same geology and structural geology apply to it all. So we're looking, this is mini shadow, let's just put it that way.
Yeah, and I think another thing worth pointing out too is like that competency contrast between the granitic rocks and those metasediments has shown to be a favorable setting for many uranium systems in the past too. So absolutely,
it's probably one of the best systems to find. You find that competence contrast between granite and metasediments. There's your fault plane, especially if you have a conductor along it. Oh, geez, beautiful structural pathway.
Okay, so then moving on to the gravity results. So these are the areas, so the structure that we identified from the mag is now superimposed on the gravity results right here. And these are a number of targets that we think are interesting. Now, suffice it to say that this is not the only map that we look at when picking these targets, and we're not going to share all of our secrets, but these are some areas of interest that we've identified so far. So then if we bring these gravity targets back onto the magnetic map, lo and behold, especially in the north, they tend to line up with some interesting breaks in the mag, which is great. In the southern domain, it's a little bit different, a little bit spottier. The other thing that we are going to do is, so this is a total magnetic image map. And so we can run some inversions on that and change it to a first derivative map or a tilt derivative map. And then those are a little bit better at highlighting the structure. So we intend to do that in the not too distant future. So then here it's the southern half of the property. It's basically the exact same story. In the north and south, we have these linear magnetic highs and lows that are our sediments. We have the granitic block in the middle, same thing, rotation, metasediments getting squeezed, and the development of the Riddell structures. And so again, repeat the process, look at the gravity, pick out our interesting targets, bring them back onto the mag map and see how they line up with the mag. Again, lo and behold, lots of interesting mag breaks that correspond with our gravity anomalies. So here's just sort of a summary. It was recently put out in a news release. So if you, on the left, here's our gravity image and then our magnetics on the other side. And so then just a little bit of a promotional thing here to zoom in on this area of interest right up here. And if we have these nice little gravity anomalies, you can see that you can easily fit some really nice deposits within some of these anomalies.
I'll point out with this image here that both of those deposits are to scale, like the individual uranium outlines. However, for triple R, the length of the deposits, or I guess the distance between each of the pods, has been kind of pushed together a little bit more than what they're in real life.
That's right.
But you know, I am of the belief that a lot of these targets that we are seeing do correspond with structures. We can't really say right now if there is any hydrothermal alteration. We're assuming so. It would be great to see that, and hopefully that our next steps will be able to help that. So we do, like you said, we look at multiple layers for exploration. We've got the gravity, and the way that matches up with our magnetics looks pretty awesome. We're going to do some additional magnetic work, just inverting the data that we have. So what else do we have to complement the results so far? What can we do?
Okay, yeah, so I guess that's the next steps. So what we're planning on doing next is, number one, an airborne VTEM survey. So this is a EM and magnetic survey that will help us pick up the electromagnetic anomalies, and we're hoping that we'll find some nice good conductors in that north part of the property. And so what happens is these EM surveys are flying, again, perpendicular to the known structure. This is a map from Pure Point Uranium over here, and you can see as the aircraft flies over top of an EM anomaly, it'll get a little ping whenever it encounters something that's electromagnetic and conducts electricity. And then as you build the flight lines together, then you get these nice trends. And then we can use these for drill targeting because we can't actually directly target uranium mineralization. So we need to layer on this data. So right now we've got our magnetics and we've got our gravity. And then next we're going to get our electromagnetics, and we're going to use all three of those data packages to zero in on our best drill targets. And to further enhance that, the next step that we're actually going to be starting in about a week is we're going to be going out and doing some ground-based mapping and prospecting over the areas that we think are interesting. And so this is basically just geologists out in the field taking structural measurements, figuring out the rock types, and also using hand scintillometers to look for any near surface radiometric anomalies. And we're going to be going out there at the start of June. And yeah, so the areas that we're going to focus on for this mapping and prospecting are basically these two up here. We really like that one up in the north with that known high grade showing, and then also with these known conductors over here. And then the next priority would be down in the south where we have these more east-west oriented metasediments and conductors. So that's where we're going to be primarily focusing our mapping and prospecting, and that'll be going right away here.
Yeah, that's fantastic.
And then, yeah, so from all of those data sets, the magnetics, the gravity, the EM, the mapping and the prospecting, we hope to generate some really good drill targets. And we are planning a 1,500 to 3,000 meters of drilling in 7 to 15 drill holes, set to begin in sometime between August and October of this year.
Looking forward to it.
Yes,
Exciting times for sure.
And yeah, just the summary. So Catharsis was staked on this large regional structural trend. There's historic findings on the project and the surrounding area that look very favorable for uranium system. Our gravity survey has given us numerous targets that can be correlated with our upcoming VTEM survey and that are going to require some ground truthing. And our summer exploration is set to start right away. We're going to be doing mapping, sampling, prospecting, and then following it up with some drilling. And I'll leave everyone to think about that last question. So thanks.
I would like to say yes, but then that would be highly promotional for us as well. But based on everything that you've just shown, and Cameron, thank you very much for giving us that rundown. Omer, thank you very much for your contributions. I would have to say that Catharsis looks beautiful. It's got a lot going for it. There's no doubt about that. The structures, you know, it looks like it is a favorable area for uranium mineralization. We've got fertile corridors. We've got high-grade occurrences in metapelites, in sheared metapelites already that has been completely underexplored. I just think there's a lot going for it, and it's, you know, it is definitely looking exciting, and you guys are going to kick some butt up in the field, and I am jealous of you guys getting up there. So what's next? What's next down the baseload pipelines? We've got a lot going on. We've completed the gravity survey over Hook, and we've issued those news results. So we will be looking at doing a similar video for Hook and updating with the gravity on that. Shadow as well. We have been looking at some new interpretations with the geophysics that we have. Plus, we have found some historic data in the area. It's not much, but it all still counts. So we will be doing a shadow update. And then I still have another video that I'd like to follow up on for the structures, fluids, and basin tectonics, and looking at fluid pathways outside of the Athabasca and how it can all contribute. We heard Cameron mention earlier that we need those low temperature fluids associated with the basin. I'm going to propose a little slightly variance to it, but it does still make sense. So maybe I'll have to get Cameron on for that one to keep me in check, because I might just be out there being a crazy guy. Regardless, we've got a lot on our plate. Things are looking exciting for the summer, and we will update as time goes on. So once again, thank you very much, Cameron. Thank you very much, Omer. And to everyone else, big thank you for watching. Stay safe, stay healthy, and please pass this video along to your friends and colleagues. And let's get the word out about baseload. Thanks all.
Thank you.